Good morning, good afternoon, or good evening, Algebra 2A, and welcome to Lesson 40, where we are going to work on the skill of simplifying radical expressions. As we continue in the second half of our school year here, we are going to use this skill as we move into looking at Pythagorean theorem, actually, in Lesson 41, and then we'll continue looking at how we can work with radicals such as square roots, cube roots, and so on in the second half of our school year. Today, our learning target is to simplify radical expressions by using the product rule or by rationalizing the denominator. So we will be simplifying radical expressions today, and then tomorrow we'll work into rationalizing the denominator, or in day 2 of Lesson 40. So a couple of new concepts to start Lesson 40. A square root. Square root of a number x is a number y such that y squared equals x. In other words, a number y whose square is the result of multiplying the number by itself, or y times y is x. In other words, 4 is the square root of 16, because if you take 4 squared, or 4 times 4, it equals 16. Now, the results of squaring numbers, these numbers are called perfect squares. So 16 is an example of a perfect square. Other perfect squares would be 25, 36, 9. Those would represent our perfect squares, and those are numbers that are square rootable, and they square root to integers. Non-perfect squares are going to square root into irrational numbers. So we have perfect squares and you have non-perfect squares. The principal root represents the positive root, or the positive answer to a square root of a perfect square. So for example, 4 times 4 was 16, but then also negative 4 times negative 4 is 16. So negative 4 is also a possible square root of 16. The radical symbol is the symbol that we use to represent roots. So we are going to use square roots, but then you also can have cube roots, quartic roots or fourth roots, and that radical symbol represents that you are taking a root. Today, we are going to work just with square roots. So we're working with those perfect squares and simplifying square roots. The radicand is the part that's underneath the radical symbol, and we're going to look to simplify perfect square factors that are underneath the radical. So radicand, it's important to know that the radicand can be simplified. And lastly, a radical would just be the whole piece put together. So an example of a problem that we may see today would be like the square root of 9x squared. That would represent a whole radical. So there would be an example of a problem that we'll look at simplifying today. As we start to introduce square roots, we're also going to talk about the possibility of cube roots, quartic roots beyond square roots. So those are called nth roots. So given that a and b are real numbers and n is an integer greater than 1, if a to the n equals b, so this would be like from above, if 4 squared is equal to 16, then 4 is the square root of 16. So that would be an example of a square root like we looked at above. And this would represent then any degree beyond squares. So like if we had 4 to the third power, that equals 64. That's going to mean that the cube root of 64 is equal to 4. So that would be that original root there that we were taking to the third power. So we will continue to sprinkle in talking about these cube roots and so on. But today we're looking at square roots. The index is this little number that's up in the radical sign, and it represents the degree of the root that you are taking. So we are dealing with square roots. It's important to know that square roots, you don't have to put a number there. So that would just be a 2 there, even though we don't have it written there. That would be a 2. And then if it's beyond a square root, we'll start putting in those little numbers to represent what degree root we're taking. So like this cube root just means that you're going to be multiplying a number 3 times to equal back to that answer of 64, and that would be that number 4. And all we're doing today is when we're dealing with square roots, we're looking for, like in this first example, we're looking for what number times itself is going to equal back to that 0.16. So square roots, we're just looking at what number squared is going to equal that 0.16. So in this example, this is like very similar to doing the square root of 16. And then since my answer has 2 decimal places in it, that means that both numbers that I'm multiplying need to have 1 decimal place, because when we multiply 2 numbers that have decimal places, our answer is going to be the total amount of decimal places that are in the 2 numbers that we multiply. So 0.4 times 0.4 is going to be 0.16. So that would just means that my answer is going to be 0.4. And I'm just going to give the principal root. So just giving the positive root. Next, we have the square root of negative 25 over 64. Now, mathematically, there's no way that we can multiply 2 numbers by themselves and equal a negative. And let me rephrase that. There's no way that we can multiply a number by itself and get to a negative, because when you multiply a positive times a positive, that's a positive. Or if you multiply a negative times a negative, that's going to still be a positive. So this one is just going to be no solution. Or you could say not possible, anything like that. No solution to that one. Square root of 64, what number times itself is going to equal 64? That's going to have to be 8. And again, I'm just going to give that principal root. And lastly, we get to our variable parts. So I have 2 numbers. And excuse me again, I've got a number times itself needs to equal y to the 6th. When we're multiplying variables that have exponents, to get to y to the 6th, the exponents need to be added together. And the second piece of information is that these 2 numbers that I'm multiplying to get to y to the 6th, they have to be the exact same number. So really what I could do is I could just take whatever that exponent is just cut that in half, and that is going to be my result. So that's the number if I take y to the 3rd times y to the 3rd. That's going to equal to y to the 6th, because 3 plus 3 is going to add to an exponent of 6. So when we're dealing with variables, and we'll head after the lesson here, we'll head over to Delta Math and look at it. But when we're dealing with variables, to find out what the square root of that power is, we can take that exponent and we can cut that in half. So looking at some additional examples. So here I just have the square root of x to the 10th. So square root of x to the 10th, to find that, we're going to take that power of 10. We're going to figure out what it is cut in half. That would be 5. So then 10 to the 5th times 10 to the 5th, that's going to multiply back to, let me rephrase that. I guess I didn't have my Wheaties this morning. Sorry about that. That should have been a x to the 10 over 2. And then that's going to equal x to the 5th, because x to the 5th times x to the 5th is going to equal x to the 10th. Now we can also look at variables with numbers. So here we have a 25 x to the 4th. So square root of 25 is going to be 5. X to the 4th, we cut that 4 in half, is going to be 5x squared. Now lastly, we get a square root of x to the 9th. Now you're looking at 9, and if you cut 9 in half, you get 4 and a half, which we need to have integer answers when we're starting to do these square roots. But what we're going to do when we have an odd exponent is we're going to think of x to the 9th as x to the 8th times an additional x. So really, when we're doing square roots, we can only take the square roots of even exponents, because those are perfect squares when it comes to variables. So we're going to think of what is the closest even number under x to the 9th in this case, and that would be x to the 8th. So then we can take x to the 8th, that ends up being square root of x to the 8th is x to the 4th. And then since a plain x is not enough to make a perfect square, that is going to be left underneath the radical. So I just call that the leftovers. So x to the fourth is what we get when we square root the x to the eighth, and then we have leftovers of square root of x. So that would be our result, x to the fourth root x. Finishing up looking at radicals, when we are dealing with square roots or any cube roots, fourth roots, when you have two roots with the exact same index, you can multiply their radicand. So for example, if I have a square root of 3 times a square root of 6, I can multiply that together to make square root of 18. So this only works if we have two radicals that have the exact same index, which we are going to be dealing with just square roots, so we'll be able to do this. The second thing is anytime we have a radicand that has perfect square factors, we can take the square roots of those out. So 18 is the result of taking 9 times 2. It has a perfect square factor of 9 right here. So we take the square root of 9, that's going to come out as a 3. But then similar to above where we had like a leftover x, we still have a leftover square root of 2. So 2 is not a perfect square. So that would represent the leftovers. So it'd be a good idea to list out all the perfect squares if you don't have them memorized, so that you can start hunting for those perfect square factors. So next, 75. Anytime I see, like, I think of this as money, this is like 3/4, 75 cents. So that's going to be 25 times 3. So I'm going to take and think of that 75 as 25 times 3. Now I can take the square root of 25, which is 5, and then I still have a root 3 left over. So there's going to be my result, 5 roots of 3. And then lastly, square root of 176. Square root of 176, since it's a little bit bigger number, you may want to take out your calculator, but I'm going to try 16 to see if it's divisible by 16. And it is. It's going to be the result of 16 times 11. So you can take out your calculator and start with higher perfect squares, like maybe start with 36 and see, is 36 divisible into there? 64 possibly is divisible into there, but I found that 16 was divisible into there. So 16, when I take the square root of 16, represents 4, and then I'm left over 11 underneath my radical. So 4 roots of 11 would be my result. Lastly, we'll start looking at when we have a number and variable combined. So here we have 18x to the third. So I'm going to rethink of 18 as 9 times 2 because 9 is a perfect square. And then think of x to the third as x squared times x. And then what I like to do is just circle. There's a perfect square, so I can square root that. There's a perfect square, so I can square root that. Square root of 9 becomes 3. Square root of x squared becomes x. And then now I still have to place my leftovers underneath my radical. I can't square root 2, can't square root x. Those stay inside underneath my radical. So there's how we could start looking then at when we have numbers and variables. We're kind of combining what we did in example 1 with example 2, starting to look at how we can simplify those. So that finishes up day 1. Tomorrow we'll look at like radicals, but you are ready to get started on your practice, and you can go ahead and good luck. See you next time.